So there was a question about the results of our little boundary value problem around the Poynting effect. And the question was, how come we have a kinematic field which is actually volume preserving? And I'll show you that it is indeed volume preserving. But the result we arrived at showed that in general, we get a non-zero hydrostatic stress. Okay, so the point is that simple shear kinematics right, which is of this form. Okay, satisfies, okay, it satisfies no volume change. Okay, the volume change ratio is, the volume ratio is 1. Okay, yet the hydrostatic stress right, in general it's non-zero. Okay, the reason here is that while we have a completely general form for the stress tensor for hyperelastic isotropic materials, we've left it completely general, right? We've not made it more specific. Now, many of the strain energy functions that we have worked with in the series of, in the course of these lectures have a further assumption that the volumetric and so-called deviatoric responses are decoupled. So let me just put that down, okay? Sigma, when written in this form, right, where the alpha i's are functions of our principal invariants. Right, this is a general form for sigma for isotropic materials, isotropic hyperelastic materials. Okay, there is no further separation of the volumetric Okay, by volumetric we mean volume changing part of the response, right? So there's no further separation of the volumetric and deviatoric response. Now I recognize that we haven't truly defined these, okay? But let me give you a very quick definition of these, okay? So when we look at F, we could write F as F bar, F tilde, okay? All right, there is this decomposition, a multiplicative decomposition that we can write, okay? Where we would say that F bar is determinant of F to the 1/3 times the isotropic tensor. Okay? Now, if you look at just this part as a deformation gradient, what you're saying is that it has the right volume change, because if you compute the determinant of f bar, you get back the determinant of f. Okay, and that 1/3 takes care of it. All right? But it is an isotropic response, which really refers to something just swelling up, right? It's as if I take this ball and I say that, all right, I look at all the deformation that this ball is going through, I compute the volume change, and I say that this f bar is a deformation, which is just a swelling deformation, right? It's isotropic, so it's sort of swelling, it's swelling uniformly in all directions, okay? But it has the right volume change, okay? And then f tilde is everything else, okay? And how would you get f tilde? Well, if you already know what f is, f tilde then is just, what is it? It's just 1 over determinant of f to the 1/3. Okay? Now, what happens with determinant of f tilde? It's volume preserving. Okay? By construction. So this is a decomposition. The f bar is considered is what you may call the volumetric part of f. Okay? F tilde is what we would call the isochoric part of f. Right? Isochoric meaning something that happens at constant volume. Right? Isochoric processes are those that take place at constant volume. Okay? So this is a decomposition one can always apply upon the kinematics. The analogous decomposition on the stress is the following. Okay? So we can now write the stress as sigma is 1/3 trace sigma times isotropic tensor plus another component that we will denote as sigma sup d. Okay? This is just the hydrostatic stress. Okay? And sigma d is what gets called the deviatoric stress. Okay? Observe that sigma d has the property that trace of sigma d is 0 by construction. Okay? It's because trace of sigma is equal to the trace of the first component in this additive decomposition. All right? So, what is usually done in many strain energy functions is to model these two parts of the stress differently, right? Differently, or saying that in a more relevant manner, you choose a strain energy function so that the hydrostatic stress P, right? Right? That's hydrostatic stress depends only upon the volumetric part of F, right? Whereas the deviatoric part of the stress depends only upon the isochoric part. Okay, that's usually done in many of these strain energy functions, and it can be detected in the strain energy functions that some of the strain energy functions that we've worked with. Okay, so so this volumetric okay, So the idea is that you choose psi tilde, which depends upon the invariance of B, if you have a hyperelastic isotropic material, okay, such that when you go ahead and compute sigma from this, okay, and that's a general result for isotropic materials, it always holds, right? But you choose psi tilde, psi double tilde such that now when you go ahead and compute sigma, okay, what you get is P finally depending only upon F bar, right? And remember P is 1/3 trace of sigma, okay? You construct psi double tilde such that now when you compute sigma from this and you go ahead and compute its trace, you will discover that the trace depends only on the F bar component, right? Well, F bar would give rise to a B bar and so forth, right? But then you can follow that change down. Whereas sigma deviatoric, okay, then becomes a function only of F tilde, or appropriately the corresponding parts of P. Okay. When this is done, we really see this this proper decomposition of the volumetric and isochoric parts of the response reflected in the hydrostatic and deviatoric parts of the stress. We haven't assumed that in our general form for sigma.